An interstellar object just did something that, statistically speaking, should not happen. Not once, not twice, but as a perfect chain of coincidences stacked on top of each other with odds so small they border on absurd. 3I Atlas has completed its closest approach to Earth and is now heading toward Jupiter. But the way it did so has left researchers, analysts, and independent observers staring at their screens in disbelief. This isn't about a single anomaly or a strange image taken out of context. It's about a sequence of behaviors that align with an almost surgical precision, geometrically, dynamically, chemically, and temporally. When you step back and look at the full picture, what emerges isn't just something unusual. It's something that forces us to ask whether probability alone is enough to explain what we're seeing. Stay with me, because once you understand what happened during this close approach and why Jupiter suddenly matters, the story changes completely. One of the most striking observations comes from images showing an anti-tail as large as the main tail itself, something that simply does not happen in normal comets. This anti-tail was measured at over 500,000 kilometers in length, longer than the distance between Earth and the Moon, and it wasn't diffuse or chaotic. It was narrow, sharply collimated, opening at an angle of only about 8 degrees before perihelion. That alone is extraordinary, but what pushes it into impossible territory is its behavior over time. The jet oscillated periodically every 7 to 15 hours, consistent with the rotation of a nucleus and a highly specific emission point, behaving less like random outgassing and more like a rotating lighthouse beam. Even more difficult to explain is the fact that this jet remained active and tightly focused after perihelion, at a time when its source region was on the night side of the object, something that standard comet thermal models struggle to justify. Heat does not propagate efficiently through typical cometary material, so activity from the dark side should be suppressed, yet here it wasn't. As if the jet behavior weren't strange enough, the overall geometry of the object pushes probability to its breaking point. The rotation axis of 3I Atlas was aligned with the direction of the Sun to within less than 8 degrees, creating an unusually stable day-night configuration. Randomly, this alignment is extremely unlikely, but it gets worse. As the object passed near the Sun, its trajectory was bent by solar gravity by exactly 16 degrees, which just happens to be double the opening angle of the jet. The result is a visually perfect symmetry, where the jet appears to always point toward the Sun before perihelion, and then emerges from the opposite side afterward, without ever changing its apparent alignment. It's as if the object rotated at precisely the right moment to preserve this symmetry. Individually, each of these alignments is rare. Taken together, the probability of all of them occurring naturally drops into the realm of billions to one, comparable to winning a major lottery multiple times in a row. Then there's the composition problem. Spectroscopic data shows an unusually high presence of nickel relative to iron, a ratio that stands out sharply when compared to thousands of known comets and is more commonly associated with processed or differentiated material. At the same time, water, which should dominate a comet's composition, makes up only a tiny fraction of the detected gases, around 4%. Instead, compounds like methanol and hydrogen cyanide are prominent, suggesting either an exotic formation environment or long-term surface accumulation during an extended interstellar journey. On top of that, the way 3I Atlas reflects light is unlike anything seen before. Its polarization behavior is extreme, and its brightness increased near the Sun faster than any known comet, while displaying a distinctly blue color, even bluer than the Sun itself. None of these traits alone prove anything extraordinary, but together they paint the picture of an object that does not behave like material formed in our solar system. Now comes the part that reframes the entire story. After passing Earth, 3I Atlas is heading directly toward Jupiter, not just casually passing by, but approaching the planet at a distance remarkably close to Jupiter's Hill radius, the region where Jupiter's gravity overtakes the Sun's influence. This is a very specific boundary, and crossing it allows objects to be captured, redirected, or stabilized with minimal energy. What makes this timing even more unsettling is that Earth itself will pass through nearly the same region of space shortly afterward, meaning we will traverse the exact corridor the object just occupied. Whether one interprets this as a coincidence, a debris trail, or simply an orbital curiosity, it is undeniably rare. And all of this happens while data from major professional telescopes remains limited, leaving amateur observations as the primary source of detailed imagery. For now, there is no definitive evidence that 3I Atlas is artificial, but there is equally no precedent for an object displaying this many coordinated anomalies while remaining entirely benign. What we do know is that it has completed its close encounter with Earth. It is moving toward Jupiter exactly as predicted, and the most important phase of its journey may still lie ahead. One of the least discussed but most unsettling aspects of 3I Atlas is its trajectory through the solar system. The path it follows lies remarkably close to the same plane in which the planets orbit the Sun, something that is statistically unlikely for an interstellar object arriving from a random direction in space. Interstellar visitors should come in from all angles, like cosmic darts thrown blindly at a spinning target. Instead, 3I Atlas arrived almost neatly aligned with the planetary disk, slipping into the solar system in a way that minimizes chaotic interactions and maximizes stability. Even more curious is the timing of its arrival. When it was closest to the Sun, the moment when the most dramatic changes could have occurred, it was effectively unobservable from Earth. Only space-based instruments had limited visibility. That means the most critical phase of its journey happened largely out of sight, and only afterward, once it had already passed the key point, did it become clearly visible from the ground. This sequence alone raises eyebrows because it feels less like random timing and more like a narrow observational blind spot. The jet behavior deserves far more attention than it has received. In normal comets, jets erupt where sunlight heats exposed ice, and as the nucleus rotates, those jets appear and disappear in complex, often chaotic patterns. With 3I Atlas, the behavior is radically different. The jets are not only extremely narrow and long, reaching hundreds of thousands of kilometers, but they also appear to activate only when facing the Sun, even when the source regions are expected to be on the night side for extended periods. This creates a scenario that is extremely difficult to reconcile with standard thermal models. Heat should diffuse, activating nearby regions, but here the activity seems selectively gated. The periodic wobble of the jet occurring on a regular time scale, tied to rotation, implies a very specific and stable emission point, as if the structure of the nucleus itself enforces this behavior. The result is an outflow pattern that looks less like random sublimation and more like a controlled release governed by geometry and rotation. Independent analyses of brightness distribution have revealed something even stranger beneath the visible coma entails. By examining intensity contours pixel by pixel rather than relying on standard visual imagery, researchers have identified multiple distinct layers of structure: an irregular outer layer associated with diffuse coma, a more circular intermediate layer, a repeated composite structure deeper in, and finally an inner core that consistently adopts a tetragonal shape. The key detail is not just the geometry itself, but its persistence. These shapes repeat across different dates under different viewing conditions, implying a coherent internal organization and a stable rotation state. Objects with small, loosely bound nuclei do not behave like this, especially after a close pass to the Sun. Thermal stress and outgassing should alter the structure. Yet 3I Atlas appears almost unchanged, as if its internal architecture is far more rigid and ordered than that of any known comet. Perhaps the most intriguing coincidence lies not in where 3I Atlas has been, but in where it is going and where we will be shortly afterward. As the object heads toward Jupiter, it passes near the planet's hill radius, the gravitational boundary, where Jupiter dominates over the Sun. This region is dynamically important, a place where objects can be captured, redirected, or shed material with relatively little energy. What makes this remarkable is that Earth will later move through nearly the same region of space, crossing close to the path 3I Atlas just traveled. Even from a strictly skeptical standpoint, this raises the possibility of residual material, debris, or simply a dynamically interesting environment left behind along that corridor. It doesn't prove anything on its own, but it adds another layer to an already dense stack of coincidences. Once again, nothing here demands an artificial explanation, but the sheer number of aligned factors makes it increasingly difficult to dismiss the entire sequence as mere chance. One of the most persistent red flags surrounding 3I Atlas is its chemical makeup, because chemistry tends to be brutally honest. Spectroscopic data points to an unusually high concentration of nickel compared to iron, a ratio that simply does not line up with what we see in the overwhelming majority of known comets. In thousands of cataloged objects, iron typically dominates, or at least tracks closely with nickel. Yet here the balance is skewed in a way that immediately stands out. At the same time, water, the defining component of cometary ice, appears in surprisingly low quantities. Roughly 4% of the detected gases are water, while compounds like methanol and hydrogen cyanide are far more prominent. That combination suggests material that either formed under very different conditions or has been chemically altered during an exceptionally long interstellar journey. This is not what solar system comets look like, and the more you compare the data, the harder it becomes to argue that this is simply a familiar object wearing an unfamiliar coat. Beyond chemistry, the way 3I Atlas interacts with light introduces another layer of strangeness. Its polarization signature is extreme, far outside the range observed in typical comets, and its brightness increased near the sun faster than any comparable object on record. Even more unusual is its color. Instead of reddening as dust production increases, which is what we normally expect, the object appeared distinctly blue, bluer than the sun itself. That implies a dominance of very fine particles or an unusual surface or gas composition affecting how light scatters. No known comet displays this combination of polarization, brightness acceleration, and color. These are not subtle deviations. They are outliers. And when multiple outliers cluster around the same object, they stop being noise and start demanding an explanation. Then there's the physical scale of the object itself. 3I Atlas appears larger, more massive, and faster than the other interstellar visitors we've identified so far. That alone raises a statistical problem. If objects of this size and speed are common enough to pass through the inner solar system every few years, then interstellar space should be filled with them, far more than current models predict. Some researchers have pointed out that our detection methods may be biased toward finding only the largest and fastest interstellar objects. But even accounting for that, the numbers feel uncomfortably high. Either our estimates of interstellar object populations are wildly off, or 3I Atlas represents a class of objects that is rarer and more extreme than we anticipated. Neither option fits neatly into existing frameworks, and both suggest gaps in our understanding that go well beyond a single anomaly. What ties all of these observations together is stability, or more precisely, the lack of expected instability. After passing close to the sun, most comets show clear signs of stress, changing activity patterns, fragmenting, or altering their structure as thermal forces take their toll. 3I Atlas did none of that. Its overall geometry remains strikingly consistent. The jet structure, the anti-tail alignment, and the internal brightness patterns persisted across observations separated by time and viewing angle. Even detailed pixel-by-pixel contour analyses revealed repeating shapes that did not degrade or reorganize after perihelion. For an object subjected to intense solar heating, this level of structural persistence is deeply unusual. It suggests a robustness that is difficult to reconcile with the loosely bound, fragile nuclei typical of comets, reinforcing the sense that we may be dealing with something fundamentally different from what our comet models were built to describe. At some point, coincidences stop behaving like coincidences and start behaving like a pattern. With 3I Atlas, what's unsettling isn't a single rare alignment, but how many of them stack without canceling each other out. The arrival direction, the orbital plane alignment, the timing of invisibility near perihelion, the symmetry of the jets, the curvature of the trajectory. All of these events should statistically dilute one another. Normally, when one unlikely thing happens, the next one breaks the pattern. Here, they reinforce it. Each new anomaly seems to lock into the previous one, creating a chain where geometry, timing, and physical behavior appear unusually synchronized. From a purely probabilistic standpoint, this is where astronomers become uncomfortable because probability theory expects randomness to smooth things out. Instead, randomness here seems to concentrate. Jupiter's Hill radius isn't just an abstract boundary from celestial mechanics textbooks. It's a dynamical sweet spot where gravitational influence changes regimes. Objects entering this region can be temporarily captured, redirected, slowed, or have material stripped away with relatively small energy exchanges. The fact that 3I Atlas approaches Jupiter so close to this boundary is, at minimum, dynamically interesting. Many trajectories miss it entirely by vast margins. Passing near it doesn't require intent, but it does require precision. What makes this more intriguing is that such regions are exactly where natural and artificial dynamics blur, where chaos and order coexist. From a natural perspective, this could simply mean gravitational reshaping. From a purely observational perspective, it means this next phase of the object's journey may reveal changes we haven't yet seen, making Jupiter not just a destination, but a test. Another uncomfortable aspect of this story is not what we're seeing, but what we aren't. The lack of timely high-resolution data from major professional observatories leaves a noticeable gap. Most of the detailed morphological information we have comes from amateur astronomers using long integrations and careful processing. That's not a criticism of institutional science. It's a reflection of how slow large systems can be when confronted with fast, anomalous events. Proposal cycles, scheduling constraints, and competing priorities all work against rapid response. The result is that an interstellar object displaying unprecedented behavior passed through its most informative phase with limited professional scrutiny. That silence amplifies uncertainty because absence of data often gets mistaken for absence of phenomena. After all the observations, measurements, and analyses, one thing remains consistent. 3I Atlas refuses to settle into a comfortable explanation. Each attempt to simplify its behavior introduces new inconsistencies elsewhere. Explain the jets, and the chemistry becomes a problem. Explain the chemistry, and the geometry breaks. Explain the geometry, and the timing feels wrong. This constant trade-off is a classic sign that the underlying model may be incomplete, not wrong, but insufficient. Objects formed in other stellar systems may carry assumptions we haven't yet learned to question. And as 3I Atlas continues its path toward Jupiter, it carries those unanswered questions with it, unresolved, persistent, and very much alive. So this is where we end up once we strip away speculation, emotion, and the temptation to jump to easy answers. An interstellar object entered our solar system, past Earth, and is now heading toward Jupiter. And along that journey, it displayed a combination of behaviors that individually might be rare, but collectively push probability to its limits. An anti-tail as large and as collimated as the main tail, jets that remain active on the night side, a rotation axis aligned almost perfectly with the sun, trajectory curvature that matches jet geometry with eerie precision, a chemical composition that doesn't resemble known comets, light behavior that defies the catalog, and a structural stability that should not survive a close solar encounter. None of this, taken alone, proves anything extraordinary. But taken together, it paints a picture that refuses to settle. What's important to say clearly is this. There is no solid evidence that 3I Atlas is artificial. None. And pretending otherwise would be dishonest. But there is also no precedent for a natural object displaying this many coordinated anomalies without forcing our models to bend uncomfortably. Right now, the most honest position is not certainty, but caution. Not belief, but attention. Because science doesn't advance by declaring mysteries solved prematurely. It advances by admitting when the data doesn't quite fit. As 3I Atlas moves toward Jupiter and approaches the planet's Hill radius, the story is not over. That region is dynamically sensitive, a place where gravity reshapes trajectories and where changes, if they're going to happen, are most likely to reveal themselves. At the same time, Earth will pass through nearly the same corridor of space the object occupied, adding yet another layer to an already dense web of coincidences. This doesn't mean something will happen. It means we should be watching carefully. What this object has already done is expose a deeper issue. Our classifications, comet, asteroid, active, inert, are built almost entirely on objects formed in our own solar system. 3I Atlas is not from here. It carries a history forged around another star under conditions we've never directly observed. Expecting it to behave exactly like local debris may be the real mistake. The anomaly might not be the object itself, but our assumptions about what interstellar objects should look like. For now, the data we have suggests something extremely rare, extremely unusual, and most likely natural, but not normal in any sense of the word. The absence of definitive measurements from large telescopes leaves us in a holding pattern, waiting for the next phase of its journey to provide clarity. Until then, the only responsible approach is to keep questioning, keep observing, and resist the urge to simplify what is clearly a complex phenomenon. If you want to stay informed as this story develops, especially as 3I Atlas approaches Jupiter and new data finally arrives, make sure you're subscribed. Because whether this object ends up redefining our models or simply expanding them, one thing is already certain. Interstellar visitors are forcing us to confront how small our sample size really is and how much we still have to learn about what's out there. And next time an object like this enters our solar system, maybe we'll be ready to understand it before it's already on its way out.